there's kind of two paths we could take today. You have enough at this point where I can introduce what I wanted to introduce, which is the variant of the row calculus, where we can start to talk um, a lot more about space. Um, and we can also talk about how space and time begin to interrelate. Um, and this is uh, in connection with the equation, the domain equation that I talked about last week, where where there's a where we have this mutual recursion going on between locations in a term and the evaluation of terms. Um, but I also want to talk a little bit about a little bit more about why these calculi are so effective. And we've done a little bit with respect to the use of the calculi to represent low-level computational phenomena like addition, and relatively high-level computational phenomena like the process calculi. Also, with the addition example, we showed that if we factor the addition, if we factor our notion of addition correctly, we get something that's much, much, much more general than simply addition, but covers a very wide range of phenomena. And which shows that, again, this is an incredibly powerful technique. But there's a lot more to the power of the technique that we haven't touched on, except only in passing. So what I'd like to do before presenting the sort of row calculus in space idea, I'd like to talk a little bit about the whys and the wherefores of these calculi in terms of the notion of equivalence. So I'm going to first just introduce the notion of bisimulation and relate it to papers that people have probably seen. Again, as with everything process calculi, it's sort of like Go in the sense that you can give these little one-liners, and they look pretty innocent as rules in a game, but they're exceptionally powerful. So with bisimulation, what we do is we introduce a notion of observation of our computation and relate observation to behavior. So bisimulation kind of starts in a world that's sort of post-classical with respect to physics. So the understanding is that observation impacts the system, it sort of shakes the system, and forces the system to evolve in some way. And this makes a lot of sense if we think about the physical world. If I have some chemical substance and I want to test it for a property, typically I might have to use up some of that substance, burn it or expose it to some other reagent, and thereby use up some of it. And I think a lot of people have a slight misunderstanding of the Heisenberg uncertainty principle, but that sort of folklore understanding that observation changes the system is spot on when it comes to the intuitions that underlie bisimulation. So somehow observation relates to behavior. By the way, this is also very, very much at the heart of taking measurements in quantum mechanics. Before the measurement, we're looking at a system that's in superposition, or some some component of it is in superposition, meaning there are a lot of possibilities as to how resources might be distributed in the system. And after measurement, that one of those possibilities in terms of the distribution of resources has been selected. So again, if I might recommend it, we mute unless we're talking. So again, the point is that this intuition about observation and the behavior of systems is closely related to how we think about physical systems. So once we have this notion of observation and how it relates to behavior, then we can define by simulation in the following way. We say that that P is bisimilar to Q, or more generally, if a relation S is a bisimulation relation, if whenever so that would look something like this. And it's kind of important to understand these. So I have some relation S, and P is S is P is S related to Q, if and only if for all alpha, if alpha, if we can observe P with alpha causing it to move in a single step to P prime, then we can find a Q prime such that we can observe Q via alpha, causing it to move to Q prime, and P prime is S related to Q prime. And then we can treat bisimulation as effectively the maximal, the union of all of these different S relations. So that's given in terms of this definition here. So it's somehow a greatest fixed point. It's the union of all S relations, all the ones that have this property. And that is an important understanding of bisimulation, and in particular, it's important when we think about bisimulation proofs.
I have a quick question.
Yeah.
In the row calculus paper, the second arrow from Q to Q prime, was that an eventually reduces? And is it not an eventually reduces here?
In this one, I'm describing strong
Okay,
bisimulation versus weak bisimulation. So
thanks.
that's a great question, because it opens up the fact that we can weaken how many steps we are allowed to take, which allows for P and Q to kind of evolve at different rates, so to speak. And it allows us to sort of relate, a kind of synchronization skeleton that the observations pick out, versus fine-grained evolution, which we might want to ignore. So that's a very important question that you've asked there. So if we want to relate it to some of the papers I know you guys have been looking at, the idea of commitment and the commitment relation in Milner's polyadic pi calculus tutorial paper is the notion of observation in that paper. So commitment is the commitment relation. And then there's a corresponding variation of this definition there. When we look at asynchronous calculi, the barb is the notion of observation. So in the row calculus paper, we describe the notion of a barb, and then we relate barb to the observation, to this relation which connects observation and evolution of the system. And and then in the work of Milner, Leifer, and Sewell, what they do is open up a whole world of connections between category theory and process calculi. And I want to go into that in a moment, but I want to stop here and check in with everyone to see if everyone's sort of following along with what's going on. So, any questions about what I've said so far?
I guess I have a question about bisimulation in the RoCalc paper in general.
Sure.
So in it seems like our notion of observability in the PyCalculus, and I'm pretty sure in the RoCalculus too, depends on like a set of names that you're observing over.
Yes.
Okay, and then also it seems like being observable at a channel, it doesn't really matter what's on the other end of that channel or what's being sent across that channel. It just matters that something is being sent across that channel. And I guess
It does matter. It does matter because you will get substitutions, and based upon those substitutions, your subsequent states may or may not be bisimilar.
okay, yeah, sure. So right, if you're just throwing away the output, then it doesn't matter. Okay, yeah, yep. Cool. Thanks.
Cool. Yeah, sure. So let me just grab, hang on a second. I want to draw a picture so that people can see what's really going on. So basically, what we're saying is that if if I can observe P via alpha, so let me get a connection here. Okay, so we've got that. And what we're saying is this is an alpha. Oops, let me go grab an alpha. Then we can find a Q prime such that if I observe, come on, if I observe Q via alpha, get to Q prime, and the subsequent states I get to are also bisimilar. So that's the picture. So for any alpha that allows me to get from, for any alpha, if I can observe P via alpha, and that takes me to P prime, then I can find a Q prime such that I can observe Q via alpha, get to Q prime, and the subsequent states are bisimilar. So what this does is it unfolds the tree of computations or the graph of computations and walks them, right? So we can we can mimic the graph of computations here with the graph of computations here. That's the basic idea. Now, um, this works for lots and lots of different calculi. So Abramsky shows that we can do the same thing for the lambda calculus, where our notion of observation is given in terms of application, right? Application in the lambda calculus gives rise to our gives rise to our a kind of evolution of the system, right? That's sort of the whole point of how the lambda calculus works is when you apply an abstraction to a value, and in this case, a value could be anything, any other computation. Um, then the system evolves via beta reduction. So we can take that idea and use application as our notion of observation and build up a notion of bisimulation called applicative bisimulation. Exactly the same definition, just specialized for that notion of observation and the relation between how observation and computation interact. So this is a much more general thing than just the pi calculus. It's a it works for all of the computational calculi, right? Whenever you give a computational calculus in the way that I have described, you get a corresponding notion of bisimulation. Now, here's the rub. The question is more generally how to relate the rewrite rules to the notion of observation, so that the bisimulation is nailed down, so to speak. What we really want is we want to be able to reason equationally about processes. We want to say things like, well, if P is bisimilar to Q, then lambda x dot P is bisimilar to lambda x dot Q. So we want to be able to either pick things apart via bisimulation style equations, or we want to be able to compose things via bisimulation style equations. So that when we are and this becomes important because we want to be able to, if we're talking about correct by construction, we want to be able to argue that certain kinds of refactoring of our computations preserve behavior. Now, and again, I want people to understand that this is not just abstract stuff. If you think about the tools that we're constructing in our chain, for example, the cryptofx tools, we are quite hungry for those tools to include notions of refactoring. And in our setting, we can give incredibly powerful automatic refactoring of programs because we can build up equational proofs that the refactoring preserves the behavior. So let that sink in for a minute. What we're talking about is equipping tools like cryptofx, which we're building for our chain development, with very powerful notions of refactoring, which provably preserve behavior. And that all arises from this idea of bisimulation and the relationship of bisimulation to equational reasoning. So what Milner and Leifer provided was, first they they encapsulated a um, a folklore observation, which was that in general, for computational calculi, there's some context which, when you put a program in the context, it evolves. So let's get some interaction going here, and say, so can you think of some contexts for any of the calculi that we've been exposed to, where the context, if you place something in that context, it directly relates to evolution of the computational term of the program? Anybody? I've just talked about a couple.
Yeah, this is Kayvon. You also draw an analogy with category theory. So wouldn't like a functor or a monad be such context?
There's a relationship between functors and monads in those contexts, but here I'm talking specifically in terms of the calculi that we've looked at to date. I mean, I just mentioned one when I was talking about Abramsky's idea of applicative bisimulation. So if you look at any of the basic rewrite rules of the calculi that we've been talking about, those rewrite rules are typically expressed in terms of some context. So let's take a look at let's take a look at at a few examples. Okay. I'll get rid of this, move this down, and let's look at oh, here, I can do it this way. So if I have lambda x dot m applied to n, then beta reduction takes me over to m with n for x, right? And if I have 4 y from x p running in parallel with x bang q, and that takes me over to p with at q for y. So in this case, the context associated would be k is equal to lambda x m applied to a whole. All right, so there's my context. And in this case, here's my context. Par some whole. And in the case of the row calculus, we can do even better, right? In the case of the row calculus, we can do this, right? And that gets us, we know for a fact that that will evolve. And it will evolve in a very similar way to the way the lambda calculus evolves. right? So here are contexts which are clearly related to the evolution of the system. Does everyone see that?
Yeah.
Anyone else? Kenny, does this make sense to you?
All right. So when I was looking at this, and I'm trying to think of for the rows, which I'm most familiar with, and message passing. And so, have you described in a general term or a general frame here what's sort of like if a message comes, then something's going to happen? Is that a way to describe it as well?
Yeah, it's something. It's something like that. So what we're saying is there's a program skeleton, such that when I put Q into the hole in that skeleton, I know for a fact that we're going to get this kind of evolution.
Right. But it's a little bit more specific than that, right? Because there are some messages that don't change the system or don't change what's happening.
Right. But here, in this particular case, I've forced what you put into the program skeleton to be the message. That's
Okay.
the only hole in the skeleton. And here, the only hole in the skeleton is the argument to the function.
Okay.
Right. So that's how these two are closely related. Kayvon, does this make sense?
Yes, it does. Yes, it does. I'm trying to make an analogy with what I do know, and it's, to me, intuitively, it kind of looks like a functor where the context is to be defined. So depending on the type of how that context is going to evolve or change, you will have a different outcome.
Yes, in fact, you can get a lot more precise, and we did that last week. So the precision here that I'm striving for is that the contexts are derived via the derivative from the term formation monad. So you have a monad that's associated with the Levier theory of the syntax, and if I take the derivative, and because it's a monad, it's already a functor. And if I take the derivative of that functor with respect to the recursion variable, then I automatically get a notion of context. That's the work of Connor McBride. And in fact, there's the time willing for this class. I want to talk about a specific a fragment of computational calculi that are described in this way. But in terms of staying focused on what we're talking about here, since these contexts are clearly related to the evolution in this way, and if I go back to my definition by simulation, how about I simply take the context as my observation, right? And then, a K dot P is literally just put P inside the K. And then that gives us a notion of evolution of the system that's directly correlated to the rewrite rule of the calculus. So what Milner, Leifer, and Sewell did was to take that observation and show that the idea of sort of the hero and contender notion of diagrams in category theory gives us this really nice way of expressing minimal contexts, right? Because any old hole, any old term with a hole can potentially interact with this, but what we're looking for are sort of minimal contexts. And when we have these minimal contexts, they provide a kind of minimal observation set because there are an infinite number of contexts. And this minimal observation set provides a nice sort of bound on the alphas here, right? In the case of the pi calculus, the alphas ended up being just the names, and even those are infinite. So being able to sort of have sort of minimality with respect to our observations is helpful. It bounds like like if you think about the old adage, if it looks like a duck and quacks like a duck and walks like a duck and swims like a duck and so on, then it's probably a duck. So that's kind of the same philosophy as by simulation, right? And each of the different kinds of observations, looking like, walking like, quacking like, right? That's and what you want is, in order to be able to determine whether or not it is a duck, you'd like to be able to bound what you have to investigate before you make the determination it's a duck. Does that make sense?
Yeah.
Okay, cool. All right. So what they showed was that if you proceed in this fashion in terms of context, then you automatically derive a notion of bisimulation that is a congruence. Um, so that means it supports this equational reasoning, and that turns out to be super super important, and it also directly correlates with ladle. So to kind of um, to tip my hand in terms of where we're going. Um, we talked about the importance of equational reasoning and how the equational reasoning is good for software tools where you want to do refactoring, or you want to prove that if I substitute this component for that component because they're bisimilar, then it will behave in the same way. All right. So both substitutability and refactoring are effectively captured via our notion of bisimulation. And bisimulation gives us equational reasoning tools and exceptionally powerful proof techniques um, for being able to characterize those refactorings and those substitutability conditions. I can take this row-line contract and I can put it in place of this other row-line contract and know that my system is going to behave in the same way. It may be different because it's more efficient, or it may be different because it has different, it may cost less, or it may be different because it has a different, there's a security property that we tighten up, but it's going to behave at least in the way that we had specified the original component to behave. So that's why this is important. But sometimes we want to be able to describe uh, um, software components at a higher level. We'd like to be able to describe entire collections of software components or entire collections of programs. And we might want to do that for a wide variety of reasons. So let's talk about a few of those. I might have a specification, right? I might be approaching this from a business perspective, or from a solutions perspective in terms of requirements. So I don't really care so much about a lot of the details of implementation. So, for example, I know I need to sort um, uh, some items in my problem, but I don't uh, uh, I don't really care which kind of sorting algorithm is used, as long as it's reasonably efficient. I don't care which sorting algorithm is used. So I might have some high level characterization of sorting, um, without going into the details of the sorting. That gives us an idea of where we might use a notion of specification, and that notion of specification um, then stands in for all of the different implementation, or a particular spec rather will stand in for all of the different implementations that might suffice. So that was relatively abstract. Let me just check in and see if that idea is making sense.
Yep.
Cool. Jacob, are you tracking?
Yeah, that was me.
Oh, okay, cool.
Greg, so when you talk about something like a function, like a sort function, in the way I would program that now, I would define the function, and then I would have some list that I want to have sorted. I would pass that list to that function, and then it would happen, and then I could do that anywhere where I needed sorting.
Mm-hmm.
Is this something similar to that, where you have a notion of something you want to have happen, a behavior, and then it can be defined somewhere else?
Yeah, that's exactly right. That's the idea. So in general, in the functional world, people have talked about this in types are not generally not rich enough to kind of describe things like sorting. So if you think about even in Haskell or in Scala, where the type system is incredibly rich, you can talk about a function which takes a list of integers and produces a list of integers, but it doesn't really say that the initial list might be unsorted, and the resulting list, the input list, might be unsorted, and the resulting list is sorted. Right? It just says it takes list to list, and unfortunately, shuffle, which takes a potentially ordered list and returns an unordered list, has exactly the same signature. So with functional types, it doesn't really describe a lot of behavior. You can get some behavior nailed down, but without significantly enriching the type system, the sort of traditional functional types don't give us this notion of behavior. The Hennessy-Milner logics, which Robin introduces a variant of those in the polyadic pi calculus tutorial, and then I give a sort of richer variant, the richness of which comes out of the fact that names have the structure of terms in the namespace logic paper on the row calculus. There, your types, which are formulae, can absolutely describe behavior. And the important thing here is, how do those formulae relate to this equational reasoning here? And what I want to get across is that there's something magical going on, because we will get a variant of a formula like of a theorem that looks like this. P is bisimilar to Q if and only if for all phi, where phi is ranging over the formulae, P, oops, it's picking the wrong font. P, and I'm going to write satisfies phi. If and only if Q satisfies phi. So this turns out to be incredibly powerful. What it says is, if we reason in terms of our formulae, we are also reasoning in terms of bisimulation. And if we reason in terms of bisimulation, we are also reasoning in terms of our formulae. So it nails down the relationship between types and bisimulation. And that's why this is so powerful. It's saying that if you are using a type discipline to ensure the correctness of your programs, it's as if you were performing the corresponding equational reasoning. So that's why in the case of Rolang, what we are doing with the behavioral types in Venus, with the Venus release, Rolang will come with the full complement of behavioral types, and hopefully within that time frame, we also start to see the CryptFX refactoring tools. So what will happen is that programmers of smart contracts will be writing things like this. They'll be typing their Rolang contracts, which will guarantee them certain properties, but those can also be picked up by the CryptFX tools to suggest various refactorings.
And would those tools get better over time as people
yes,
add more? Hey, this is a really great way to refactor, what this pattern.
Exactly. That's exactly right. So it allows for the discovery and a sort of accumulation of this sort of design pattern knowledge. That's exactly right. But it's like design pattern knowledge, very souped up. Now there's a couple of pieces of subtlety. There's a couple of subtleties here that I want to point out. It's tied to, again, the power of the bisimulation relationship and the bisimulation definition. The bisimulation relationship with observation and the way we build up the definition in terms of that. In the first formulations, before we understood about this idea of using contexts as observations, it was pointed out, and for example, Kairos in his paper on the spatial and behavioral observations in a logic for the pi calculus. He points out that the ordinary notion of bisimulation, which in the case of asynchronous pi calculus is barbs, or in the case of the synchronous pi calculation looks essentially like the commitment relation. That is insufficient to distinguish structural relationships like par. So there's a theorem which Milner presents even in CCS and represents in variations of in the pi calculus, where he shows that all that under the sort of standard Com rule, all into different shuffles. It's summation over different interleavings of interaction, which means you can eliminate parallelism for non-determinism, right? So you don't know which shuffle you're getting, but you're always getting some shuffle. All right, so that's a way to interpret parallelism as opposed to true parallelism, where you literally do have multiple threads in your system. In which case, you'll get two things actually happening at once, as opposed to just some interleaving of the two things. And people following along there? The difference between shuffling versus true concurrency.
Yeah.
Cool. All right. So, and that's important. Like if you're going to implement the pi calculus, right? You know that you're respecting the Com rule. If you implement this over a thread pool and the thread pool has only one thread in it, and then if you bump up the number of threads, then you'll go from a shuffling interpretation to a true concurrency implementation. So with that idea, we can see that Kyros's spatial formulae see things that bisimulation can't see. Bisimulation can't see the par operator, because the par operator can always be removed in terms of shuffling. That's what we just said, right? So that shuffling means that bisimulation, when our observations are only include interaction at names, bisimulation doesn't respect this relationship here. But when we move things into contexts as providing our notion of observation, we can get a bisimulation that respects this relationship again. And this talks about a very general property of bisimulation. So in particular, we can pre and post compose. So remember in our formulation where we had an S relation is a bisimulation if, and then bisimulation is sort of the union of all the S relations. Well, we can pre and post compose those S relations with sort of erasures. We can sort of make the relation coarser in some sense. And just so that people are aware, there's trace equivalence, right? So if you just make sure that all the steps in the reduction relationship match, that's so you look at each step in a sequence of evolutions. then P and Q are trace equivalent if all the traces P makes are made by Q and all the traces Q makes are made by P. That's strictly weaker than by simulation in the presence of non-determinism, right? Because trace equivalence can't detect non-deterministic branching. So that's the that's the sort of argument or proof that trace equivalence is weaker than by simulation, but you can recover these weaker forms of equivalence, composing your bisimulation relation with a sort of coarsening relation after the fact or before the fact. So there's a paper from 2005 which shows that all of the proposed notions of equivalence with processes factor through bisimulation, meaning that they look like a pre or post compose of the bisimulation relation with the with some weakening or coarsening of the relation, and that's an incredibly powerful idea, because once again it exposes bisimulation as this sort of cornerstone or like core building block of our notion of what computational equivalence can and should be. And then, if you recall, I related this idea on the one hand to the way we think about the equivalence of physical systems in physics, but also in terms of our common sense understanding of, when two things are the same, right? So it looks like a duck, walks like a duck, quacks like a duck, those sorts of things. That basic idea from sort of common sense philosophy or folklore philosophy is sort of captured in bisimulation. So bisimulation sits at the heart of all notions of equivalence in the process setting, and we can auto-derive it. We can auto-derive a proper notion of bisimulation for all rewrite systems that satisfy a minimal set of properties using this idea of context. And then bisimulation is correlated to our notion of formula or type in this way. And so if you remember what I was saying at the outset of this of today's class, the question was, sort of, do I go and introduce the space calculus, or do I introduce more of the whys and wherefores of computational calculi at all? And sort of what I tried to do is give you a taste of the whys and the wherefores. And say the reason we utilize this particular kind of formalism, the reason it stands out over other kinds of formalism, whether it's Turing machines or Petri nets or von Neumann machines or anything like that, is because the formalism lends itself to these extremely tight relationships. We have an effective notion of equivalence, which is correlated to a notion of observation, and which sits at the cornerstone, at the heart, at the foundation of every single notion of equivalence that we've come up with, and also correlates to our notion of physical equivalence and correlates to our notion of common sense equivalence. So it's sort of, it passes a QA standard that no other theory, to the best of my knowledge, passes. let me again, let me try to nail this down for you in very, very practical terms. If we move over to the realm of physics, what physics has proposed for the last 400 plus years is that we capture dynamics, the dynamics of systems, whether they're computational systems or biological systems or physical systems, via differential equations. And the that has had a great deal of success, right? People have been able to make calculations which allow us to check the stress on airplane wings or the stress on bridges. We've been able to make calculations that talk about the evolution of chemical solutions or the movement of the tides. So it's a very powerful idea, and yet, despite its power, if I hand Jacob one set of differential equations and I hand Kenny another set of differential equations, they will be very hard pressed to talk to me about when they are the same, when those two different characterizations of the dynamics of some systems describe the same systems. There isn't even a general theory for that.
Yeah, I could see, Greg, in that, just thinking from a scientific perspective, if we had a way of knowing when systems are the same, there's pretty much no telling what surprises there might be out there in terms of equivalence.
That's exactly right. So for example, a lot of people design security systems via biomimicry. But biosimulation allows you to take that idea many times more seriously. So you could write down, for example, a row calculus description of an immunological response to the attack of viruses, and then you could write down a row calculus description of the blockchain's response to a particular attack vector. And then you could literally check and see if those two systems are bisimilar. And we have a clear notion of what that means. Likewise, because of that, you could take your description of the immunological response and transform it via equational reasoning into a system that was a design for a security property of a blockchain, potentially, right? I mean, that's the idea. And I want to point out, because Kayvon brought this up, this notion of equivalence is actually much finer grained than the kinds of equivalences we see in category theory. So it's an exceptionally powerful notion, and lends itself to the kinds of analogical reasoning, right? Reasoning from one domain to another that was envisioned by the inventors of category theory, but it's actually it actually carries out the program again according to there's a body of evidence that it carries out the program in a more effective way than even category theory does, and that's one of the reasons why, for example, I went after the problem of knots to show that this tool by simulation can and should be used in other branches of mathematics. Morris Herlihy and Eric Goubot and some other researchers use the tools of algebraic topology to give us some theorems about concurrency. So they have a bunch of no-go theorems that are in many ways closely related to FLP impossibility, which is something that we think about a lot when we think about Casper and we think about consensus. But when I was thinking about knots, what I did was to show that the notion of knot equivalence, which arises from the Reidemeister moves, it can be characterized in terms of weak bisimulation. So you get a theorem of the form: two knots are ambient isotopic, which is the notion of equivalence in knot theory, if and only if their representations as processes are weakly bisimilar. And the goal was to not just to show that we have some new kind of knot invariant, which is many times more discriminating than the Jones polynomial, but instead is to show that the tools of bisimulation can, and in my opinion, should be imported into algebraic topology. And that's why I took that on, is to show that bisimulation is not just for process calculi anymore. It's a much deeper idea, and that's why we pick we pick the computational calculi as a way of going after and representing a variety of systems, whether they're software systems or physical systems or chemical systems or biological systems. The computational calculi have tools that just don't exist anywhere else, that have very tight relationships within themselves and to our physical and common sense intuitions. So that's the whys and the wherefores of this. And so I'm 3 minutes over. I'll stop there and turn over to Casper.
Ciao.
Ciao, guys.